A very, very, very warm welcome to Christian Johansen, who's going to be joining us or hosting this session, looking at event modeling as a learning framework. So thanks for joining us, Christian. Very warm welcome. The stage is yours.
Thank you. Thanks a lot, and hope you're doing well. Please make some noise out there. Touch the react button so I can see if you are 5 people or 70 people, and keep it coming during the talk. So yeah, the title, Event Modeling as a Learning Framework, How Information Really Flows Through Your Organization. To start, this is not an EDA, Event-Driven Architecture talk. It's more about the internal domain events inside your service or bounded context. Okay, here it doesn't claim that I know your organization. Of course I don't, and that is okay. But my question is to you, do you know how information really flows through your organization? So in this talk, I'm going to try to tell the story of how event modeling can make implicit knowledge explicit. So yeah, I joined Chronoshub recently, and as a part of an onboarding process, I was asked to formulate the essence of what Chronoshub does. And this is relevant because we will use an example from this domain. This is, we call it scholarly publishing. So before you needed to, when you submitted an article, you got it published, but before the digital revolution, that cost money. So, but it still costs money, I can tell you. So the author needs to select what we call a publishing offer, and then he needs to select a license and write and sign that license, and then that flow is finished. So that's the example we will look at. But other than that, I've spent many years trying to facilitate collaborative understanding via domain event modeling and other techniques. But the recent year, I also switched direction, trying to use event modeling as an input or a specification that AI can build against. So this leads me to this slide. Once AI makes generation cheap, the value shifts entirely to the specification. Keep that in mind. How many have seen this illustration? It's pretty well known. I think a lot of you already know it. But the point is here that event modeling also helps solve this kind of problem. So event modeling builds from previous techniques, standing on the shoulder of giants, to say user story mapping, event storming, and then event modeling. All three share one thing: you make work visible. Everyone in the room sees the same thing at the same time. So this technique helps us make information flow or a knowledge flow explicit. So what is a knowledge flow? I have a definition here. Your ability to transfer knowledge between people and technology in ways that change and shift the system. And there's another quote here. Those companies that don't adapt to understanding knowledge as a force of production, more important than land, labor, and capital, will slowly die and will never know what killed them. Strong quote. By Larry Prusak. He spent decades studying how knowledge moves in organizations, and most of it stays trapped inside the heads of individual persons. So we have a challenge here, and Diane Tallinn has another quote. She puts it plainly and well. Our biggest problem isn't configuring Kafka or Kubernetes, it's learning to think collectively. And of course, my story is to say that event modeling tries to solve that challenge. It draws knowledge out of individual persons' heads and make it visible, shared, and precise. So what is an event model? Think of it as a blueprint that works at 2 levels at once. At the top level, you have the picture movie storyboard, the complete narrative of what happens in your system in sequence that anyone in the room can follow. At the same time, at the lower level, we have all the details. Those are commands, events, read models, business rules in the form of given, when, then scenarios. So this is where some rigor kicks in. We have few building blocks, a well-defined, simple shared language that forces the team into a specific direction, making realistic, detailed examples of what the system should do. And that knowledge has to happen at some point. So the event modeling technique just makes it explicit and visible that we have to do that. So there are 4 building blocks and patterns: trigger, command, event, view, and pattern, state change, state view, automation, and translation. I will go into detail about that when we move on. And here we have a very important concept, the slice. So it's a vertical slice through the event model. Imagine the event model is a bread, and then we have a slice of that piece of bread. And that slice becomes the single smallest piece of behavior that we can hand to a developer or an agent. So let's just show this real model from the publishing offer. That's a scholarly publishing. So the user has an article accepted, and then the user need to select a publishing offer, and then the user need to sign a document. So that's quite simple. So we got an external event, and then we got all these events. And then we see the screens that the author in the author swim lane here, initiate publishing offer selection, select publishing offer, sign a license document, and then the user sees a confirmation summary. Then we add all the automations, things that happen in the background. We have some automation that have to generate the publishing offers based on the state of the article and journals and other complicated rules. And it also has to generate a license document that the user can then sign. And if the user signs, then an automation can mark this flow as complete. Then we add the commands. Those are the intent, and they're closely related to the events. Of course, the command can fail, and then we get an error. But in the happy scenario, we get events. Then we add the read models, or the output from the events. We can project or create many different read models from the same events. And those read models goes into the screens that the user see, or into the automations. The automations need data, and we formulate that as views or read models. Then we have all the given when then specs below, all the business rule that we need to define. And then we can have the slice, and this is an automation slice. This is a state view or read model slice, and this is a state change slice. And these look very similar. We could also call them write slice or command slices, and the read slices we call read slices. Let me show you something in a live tool. I hope you can see it. Can everyone see it? Thumbs up. Good. So here we have the generate eligible publishing offer command, and then we have the corresponding event. One thing we can do with tooling, this is just one of many tools, we can do what we call a data completeness check. So what if I add a new field here, plus, now we just got this red line. That means the data completeness check failed. We need to answer where the data comes from. It should come from the command, so I can just copy it up to the command, and now the command got it. But now the problem just moved, so we need to track all the way back to where the data originates, and that's good to have this tooling to do these things. Another thing I wanted to show are these given when then scenarios. So here we have a happy scenario, and you can see given all these events, when we try to issue a command, we get a new event. And there are quite some detailed data here. And the same goes for the error. Given this state of all these events, when we issue the command, we get an error, and we can define all the details, test examples, and error messages together. And we have to do it at some point, right? And we do it during the event modeling sessions. So time is running. So back to the slides. Out of these kind of tools, you can get a JSON file or another file. So the tooling has an underlying JSON file backed by a JSON schema. So every element on the board, commands, event, read models, given within scenarios, is typed and validated against the schema. So the event model is the contract between every part of the system. So the model is not only documentation, we can say it's machine readable intent. And maybe you heard that term before. I want to use an analogy here. We can compare the JSON file with a CAD file that goes into a 3D printer, and out comes a product. So once this 3D printers were very expensive, and now they have become cheap, and the cost lies in the materials for printing and of producing a CAD file. So the analogy fits how we can build software with the help of agentic AI today. So now the engineering challenge becomes, how do we build a printer of good enough quality that produces high quality products? And how do we become good at designing the CAD file? And again, the event model JSON is that CAD file. So here, I want you to take off your product design glasses. This is the double diamond with diverge to explore and converge to decide. So my point is that at some time the event model JSON becomes the conversion point. And if you put it into your production, out comes the product. The specification sort of becomes the product itself. Once we produce the specification, we also have a product. So we can say that the event model itself as a whole is a specification, but the given when then scenarios are where the real detail lives. So each slice gets we can call it behavioral contract, and we use example mapping to get there. You take a business rule and work through the concrete examples until everyone in the room agrees on what it should happen. We avoid abstract discussion. We discuss concrete, real examples. So another point is that agentic AI actually increases the demand for good code quality, because if the agent runs fast, it does, then problems compound before you can catch them. If the code quality is low, then it will just produce even more errors and even more poor code. So we did an experiment at Chronoshub. We applied code scene to our code base at Chronoshub, and we got 3 very different scores. So our legacy score scored 4.7, our platform scored 8.9, but our new agentic pipeline actually scores 9.9. And to the left, we see this Dijkstra formula. So if the module itself has 99.9% quality, that sounds really good. But if you connect all these modules, 100 modules, and in this case, 1,000 modules, then the overall system quality decays to 37%. So we really need that high quality margin. According to the code scene, if the score is above 9.4, then you're in a good place. If it's below, then the agent starts to just make more and more errors. So what we do, how do we make this high quality code then? We have 2 things I want to touch on. The first is the vertical slice architecture. Each slice is independent, decoupled, it's bounded, testable. And second, we use 80 to 90% of our code is actually code generating, that is deterministic. So commands, events, and read models are templated, and the types sort of define themselves. The only space left or wiggle room for the agent is the behavior, and that's exactly where we have the given when then scenarios, which it cannot change and say, I want to change the specs so my test can pass. No, it's not allowed to do that. So we hash those specs so we can see if something is changed. And with this quality, if we find bugs, it's probably because the specs were wrong or incomplete. You can't really blame the agent if there's something wrong. You can only point to yourself. So a lot of information on this slide, but let's start. The agent learns while it builds, that's one point. But on the right, we see this flywheel. A flywheel in mechanics represents accumulated or compounded energy. Here it represents accumulated or compounded knowledge. A flywheel has a lot of inertia. It takes energy to accelerate it, but once it's up and running, in motion, it nearly runs by itself, but only if it runs smoothly. Imagine a steam turbine in a nuclear power plant. You want to closely monitor if it starts to wear down. So this brings me to the concept of harness. A harness is everything that keeps the agent producing high quality code, and we just saw the criteria for that. So the Ralph loop, if you look at the left on the slide, the Ralph loop is an agent or a team of agents that takes one slide at a time and loops, implement, validates again, given when then, learn and repeat. So the knowledge accumulates in decisions, markdowns, and learnings markdown, these two files. And those are sort of mini architectural decision records. So we could choose to elevate them up and say, these are good decisions if you have a human in the loop and it's just not running autonomously. But the point is that the Ralph loop is a self-corrective and self-learning loop. So the real shift is not about the agent, it's about where the value is created. Again, the hard work moves to the left, towards product, towards specification. If the specification is right, the code follows by itself. So the flywheel operates at every scale. I titled one model, many learners. So at the top, we have the organization, which makes decision based on knowledge. And if we can push knowledge up to the decision maker, that is good. We can also choose to push decision power down to individual teams, individual persons, or individual agents. So the decision power could move forward and back. So one example is, for example, and if you start a new job, you're onboarding, and you struggle to get a clear picture of how the system actually works. You ask different people and you get different answers. But with an event model, a new team member could see the complete business flow on day one, all the actors, vocabulary, the boundaries, the business rules. Let's move on. Another point is that we can do event model on two systems, and those two systems are the system of use, the product you build or the service you provide, or the system of work, the process your organization runs internally. So here we can also use event modeling and make those workflows explicit. And once we've done that, we can choose to automate them if we want to. So all this is pointing to that what we have here is more than just a technique. It's the beginning of a more mature engineering discipline. So for decades, software development has been closer to what we call artisanship than engineering. We had individual skill, tacit knowledge, craft, a lot of different ways to do it. Civil engineering, on the other hand, has went through a very long transition. And the outcome that we have now in civil engineering is formal specifications, material standards, codes. We simulate, and we also have accountability. You actually have to sign that this bridge will not break down. So Martin Hussein Lidholm makes that case in his software civil engineering article. So he argues that we need to do the same shift as civil engineering did. We need to move to software civil engineering. And when you add AI speed to that picture, governance cannot be manual. It needs to be declarative and machine enforceable. That's what our InfoQ article tried to address, architectural governance at AI speed. So that goal is an efficient organization. If we look at a Wortley map, things evolves. So once AI was a new thing and now it has matured, everyone has it. This enables new value to be invented. So we think this value could be conversational AI event modeling. We think that could satisfy user need for an organization, maybe legacy modernization, or for individuals like software architects. We can achieve model-driven development, code following a standard. All these things need to mature, but that means that the underlying dependency also need to mature. So I showed you the tooling before. that needs to mature, and everyone are building tooling for this nowadays. And the schema also have to mature. So the last thing I want to point to is this quote by Marty Kagan. Let's show this. I think we will stop there. And then I just want to say thank you. And I have a last slide with more information. But that's it. Thanks for listening.
Wonderful, wonderful. I'm not sure about anyone else, but I wasn't actually hearing the audio from Marty then.
You didn't? Ah, that was bad. So then you have to...
if you could maybe just briefly summarize what he was saying.
Yeah, what is he talks about the empowered engineer, and he says that the greatest source of innovation is actually the engineer, because they have the best knowledge of what is technically now possible. And the problem is you often shield away the engineers, tell them that they should code, so they're shielded away from thinking in products, learning the domain. And we hope that event modeling can enable that, but AI can also release what you did to solve new kind of problems. I know we liked solving coding skills, but there are other problems that we can solve. So the message is become a product engineer, an empowered product engineer.
Okay. All right. Wonderful. Wonderful. Well, we're at the time limit now, so perfect timing, Christian. So thank you for that.
Yeah.
Thanks for a really, really interesting and a wonderful session.
Thanks a lot.
Good stuff. All right. The next session will be starting straight away here in the sessions area, so you can make your way there now.